Hello Calculus, we are in section 1.5, limits at infinity today. I'm going to force a pause on your screen, make sure everything on the checklist is ready to go. Alright, so a little warm up for you. Draw the graph of y equals e to the x for me, as well as y equals negative e to the x. I'm going to force a pause on your screen, hit continue when you're ready to see the answer. Alright, so I've got kind of a rough sketch of both y equals e to the x over here, which is exponential growth. And that would be the general shape, whether your base was e, or 2, or 3, or 10. And then on the right-hand side here, I've got exponential decay. Okay. One thing to keep in mind is that for the graph on the left, the limit as x approaches negative infinity of f of x. So as we go to the left forever, this way, right? What limit do we have there? That approaches 0. Similarly, the limit as x approaches positive infinity of this graph is also 0, right? As we go to the right forever, we have that horizontal asymptote at 0. All right, so today we're going to look at how do we find the limit as x approaches plus or minus infinity analytically. So not necessarily if I give you the graph, but if I give you the function as an equation, okay? Now, what I'm talking about is actually something you've already done in Algebra 2 and Pre-Calc. If I want to know what's going on as x approaches plus or minus infinity, what I'm really talking about is if I have an answer, I'm talking about a horizontal asymptote, right? And you have done horizontal asymptotes since Algebra 2. If you remember, there is an acronym, and the acronym we use is Bobo Botan Eats DC. So if you're not familiar with it, go ahead and write it with me now. So Bobo Botan eats DC. Okay, so hopefully this looks familiar from Algebra 2 and or Pre-Calc. This is what all that stands for. Bigger on bottom, not supposed to look like a 0. Bigger on top, none. Exponents are the same. We divide coefficients. Okay, so this was kind of a strategy that we used in Algebra 2 if we wanted to find horizontal asymptotes of rational functions. Remember, rational means fractional, so something over something else. And what we would do is just compare the degrees, and the degree is the largest exponent. So if your degree was bigger on bottom, over here, then you would have y equals 0 as your horizontal asymptote. If the degree was larger in the numerator on top, you'd have no horizontal asymptote. And if the exponents were the same, you would have y equals whatever your leading coefficients were when you divided them. Okay, so let's take a look. Let's see what we remember here. I'm going to force a pause on your screen. Can you go ahead and write the 3 limits I have on my screen? All right, so let's take a look at the one on the left. We've got limit as x approaches infinity, so that tells me I'm looking at a horizontal asymptote, so that means I'm going to use this strategy here, of 2x all over x squared minus 3. So degree of the numerator, your largest exponent, is an understood 1, but the degree of the denominator, again, your largest exponent is 2. So since 2 is larger than 1, you have bigger on bottom, which is this scenario here. So this limit is going to equal 0. Okay? All right, take a look at the one in the middle. Your degree of the numerator is 2. Degree of the denominator, again, your largest exponent on the bottom is 1. 2 is larger than 1, right? So now we've got bigger on top. That means no horizontal asymptote. So what do you think the limit's going to be here? Limit's going to be d and e. All right, now that last one, be really careful. Your degree of the numerator is definitely 2, right? Largest exponent. Now what about the degree of the denominator? The degree of the denominator is technically 2. Yes, you've got the 4, but it's inside a square root, okay? So that is going to be 2. Your degree is 2 for both. So I've got this exponents are the same scenario. So I'm going to divide coefficients. Now be careful again, because your leading coefficient in the numerator is certainly 2. But what is it technically of the denominator? It's actually 3, because again that 9 is inside the square root. All right, so we are going to kind of take this idea of Bobo, Bot, and EATS-TC and kind of expand on it. In calculus, we're not just going to look at polynomials or irrational functions in terms of polynomials. We're going to add on trig and exponentials and logs as well. So I'm going to force a pause on your screen, and can you, in your notes, just put common functions in order of growth rate. All right, so the functions that are kind of in the middle are what you are used to looking at from Algebra 2. Those are your polynomials like x squared, x cubed, those types of functions. Your fastest growing functions are going to be your exponentials. Okay, now the inverse of exponentials will be logs, so those will be kind of your slowest growing functions. And then I'm also going to put here sine of x and cosine of x at the very kind of bottom of the totem pole, because remember, those are just waves, so they don't grow at all. Okay, so exponentials grow faster than polynomials, grow faster than logs, grow faster than sine and cosine. Okay, so if we want to make maybe a more complete list, or not necessarily in words, I'd put like sine and cosine. And then typically the logs you're going to see will be ln of x. And then for polynomials, we know like x grows slower than x squared, grows slower than x cubed. Okay, and then your exponentials also have a rate of growth, where the larger the base, the faster it grows. So like 2 to the x is going to grow slower than e to the x, because e is about 2.718, which grows slower than 3 to the x, etc. Okay, so we're still going to apply Bobo, Bot, and we're still going to compare top and bottom, numerator versus denominator, but now we have a few more functions in our arsenal to look at. So a note about exponentials: when I'm looking at these exponentials, notice that they're all exponential growth when they're in this list, okay? The base is greater than 1 and your exponent is positive, okay? So note about exponentials. Exponential growth is what is in our list. In other words, if we have e to the negative x, we need to look at it in a different way, and we'll get to that in a bit. All right, I'm going to force a pause on your screen. Can you go ahead and copy my 2 limits? All right, so the one on the left, we've got the limit as x approaches infinity. That right there tells me I need Bobo, Bot. Okay, so let's take a look at what we have. In the numerator, I've got e to the x, and I've got an x squared. So if we go to our list over here, I can see, okay, the exponential beats the polynomial, right? So the term that's going to take over is the exponential. Okay, so that's going to be my leading term in the numerator. All right, now look at your denominator. I see I've got a polynomial and an exponential. Again, if you look at your list, you can see, okay, exponentials grow faster than polynomials. So the leading term, again, the term that takes over in the denominator, is that term. Okay, so now do you have Bobo, Bot, or EATS-TC? In this case, you've got EATS-TC because these, the 2 e to the x's are considered exponents are the same. So we're going to divide our coefficients, and the answer is 5/3. Okay? All right, let's take a look at that second one. I've got a sine, and I've got a polynomial. Which one takes over? Looking at our list, you can see that the polynomial beats the trig. So I've got a polynomial for the leading term in the numerator. Now in the denominator, I just have an exponential. So now I'm going to compare the x cubed to the exponential. So again, looking at your list, which one takes over, the numerator or the denominator? The denominator, because again, exponentials beat polynomials in our list. So I have bigger on bottom. So this goes to 0. All right, I'm going to force another pause on your screen. Can you copy what I have, please? All right, so my note about exponentials was in our list we were assuming exponential growth, but as you can see in my two examples here, now we've got some exponential decay, right? So that's why we did our warm-up. Recall that e to the negative x looks something like that, okay? So in other words, the limit as x approaches infinity of e to the negative x, so as we go to the right forever, is going to be 0. Okay, so whenever you see an e to the negative x and you want x to approach infinity, we can replace that with what? We can replace it with 0. Okay, so let's take a look at that first one. If I want to take the limit as x approaches infinity, I have these e to the negative x's. I know from that graph that piece is going to go to 0 and that piece is going to go to 0. So what do I have left? I have 2 minus 0 over 5 minus 0. So I have 2 over 5 for my limit, okay? All right, let's take a look at that second one. Again, e to the negative x is going to go to 0 as x approaches infinity, as is this part. So I have 5 minus 3 times 0 over 0. So I have 5 over 0. Remember, 0 on bottom is a no, so this limit is a d/e. All right, here is our final example. Now, what about limits at negative infinity? So our strategy here is going to be to replace any x with parentheses negative x, and then apply the normal limit. Okay, so good old Bobo Botten. All right, so let me force a pause on your screen and copy my two limits here. Okay, so I see that I'm approaching negative infinity. So what I'm going to do is anywhere I see an x, so here, here, and here, replace it with negative x, okay? So if I replace this x with negative x, I would get 2 times negative x, which would be negative 2x. If I replace this x with a negative x, I get negative x squared, but a negative squared doesn't change anything, it's still positive, right? Then if I replace that x with a negative x, I would get plus 3x. So we've replaced. Now we're going to take the limit as x approaches positive infinity. So apply Bobo Botten. So what do we think? Do we have bigger on top, bottom, or same? So we technically have exponents are the same because my degree in the numerator is 1. And yes, I have a square here, but it's inside the square root, so technically my degree in the denominator is 1 as well. So divide coefficients, negative 2 in the numerator, and what do we have for the leading coefficient of the denominator? We actually have 3 because it's 9 inside the square root. All right, let's take a look at that second one. So I see x is approaching negative infinity. So anywhere I see an x, here and here, I'm going to change those to negative x's. So we've got 2 minus 3, and I would have negative x, right? So that's going to be positive x. Then in the denominator, 4 minus 3, again, to now the positive x. We want to take the limit as x approaches just regular infinity now. All right, so what do we have in this case? Bigger on top, bottom, or same? This is another case of exponents are the same. So your leading term in the numerator is negative 3x over negative 3x. Divide those and you get positive 1. All right, y'all, I will see you next time.